Welcome to Microsoft Build 2017. My name is Joel Narwold, and the title of this presentation is Real-Time Sentiment Built on the Azure IoT Stack. For an agenda, we're going to talk about Microsoft Pulse, the real-time voting platform, the technical challenge of handling large volume scale, a walkthrough of Pulse and how it works, the numbers behind Pulse during live events, the data pipeline, how data flows from the user to the server and back again, testing the architecture, and ensuring a high level of reliability, and finally wrapping up with lessons learned, things to consider, and resources. A little bit about me. I'm a full stack developer with the GMR Marketing Digital team, dedicated to the Microsoft Pulse project. I've been with these guys for the past 2 years, and during that time I've helped support several large-scale events, including this past year's State of the Union and presidential debates. But what is Microsoft Pulse? Well, 3 years ago, Microsoft partnered with GMR Marketing, an experiential agency with a deep digital and product development team. They partnered with us with the intent of creating a bleeding-edge crowd engagement tool. The goal of that tool was to capture audience sentiment in real time and display the feedback from participants through both live voting and polls. Overall, we accomplished our goal. We were able to support a myriad of different events and producers, including CNN and Telemundo's coverage of the 2017 presidential race. When GMR partnered with Microsoft, one of the core technical challenges was how we would handle large-scale volume. We would need to accept data from hundreds of thousands of concurrent users, tally the sentiment of those users by demographic, and report the results back to users and producers in real time. Now that I've talked about the overall goals of Pulse and the technical challenge, it's time to give a little bit of a walkthrough and let you see what Pulse looks like in the wild. If this were a live event, I would send out a link to my Pulse, and this is the screen that you as a participant would see. You can see that there is a base question. Do you agree with what the speaker is saying? This question is the essence of Pulse and will remain the same over the course of the event. The goal of the question is to help you gauge the sentiment of your audience, whether they like what they're seeing or hearing or not. I'm going to go ahead and vote positive, since I like what's being said so far. The first time I vote, it's going to ask me for some base demographic information. These demographics are fully customizable by the producer and help them slice the sentiment into the segments they need to better understand the overall results. So I'm going to go ahead and vote on these. Male, 25 to 34, with an associate's degree, and I work for GMR Marketing. Once my demographic information has been saved, I'm free to keep voting, and I can do so once every 5 seconds. That 5-second interval is set by the producer and can be as long or as short as you want, but we found 5 seconds to be the optimal number. The blue line that's being drawn is the overall sentiment of the Pulse. This sentiment is an aggregate, not just of my votes, but also the fake data that I'm pushing through our test suite. Thanks to our test suite, I'm actually one of roughly 600 users currently voting on this Pulse. I have the test suite voting against this Pulse so I can give you a better idea of what data looks like and how we can break it down. If you're curious about what that test suite looks like, stay tuned because I'll be demoing that toward the end of this presentation. I'm going to go ahead now and switch to the producer screen so you can get a better feel for what they see during a live event and how they might interact with the Pulse. On the producer screen, you're going to see the same Pulse graph that the second screen users are viewing, and you can slice the data up by any of the available demographics. Unlike the second screen though, you get an overview of the traffic that's hitting your Pulse. In this instance, you can see that I have 601 unique visitors. 600 of those are simulated test users, and one of those is me. If you're trying to get into slicing data into useful demographics, you can do that with the filter here. As you select a demographic, you're going to see different colored lines representing the demographics within the grouping, and you can select as many or as few of those demographics as you want. This is especially helpful when you want to focus on a particular group during a moment within the Pulse. For example, during some of the presidential debates, it was great to see how Republicans, Democrats, and Independents reacted when different candidates were speaking and how those reactions differed from other groups. So I'm going to give you a little bit of an example here. If I go into education and I want to see how high schoolers and associate's degrees view what I'm saying, I can just filter out everything else. And the lines that I'm seeing here are only high school and associates. So you get a good feel for what they're thinking and how that compares to each other. Keep in mind that what I'm showing you right now is just a snapshot of Pulse, and the producer screen does so much more than just monitoring the event. It's a self-service tool that allows a user to create pulses, surveys, and polls and monitor each of those as they're pushed to the second screen. And as you saw from the dashboard, producers can gather valuable insights on how many users are viewing their Pulse, the number of votes that came in, and how different demographics are voting. We've talked about Pulse, what it is and how it looks, but what about how it performs in the real world? To answer that, let's look at some of the numbers behind live events that have been supported by Pulse. One of these was the 2016 Iowa caucus. During that event, there were roughly 21,000 unique active users, 29,000 overall, and 315,000 total votes. The difference between unique and unique active is that unique active represents the max number of users that voted in the same interval. Essentially, there was an interval during the caucus where 21,000 users voted during the same exact interval. Unique, on the other hand, represents the total number of users that visited and voted on the Pulse at least once. A slightly larger event was the 2016 State of the Union. For that event, we saw 124,000 unique active users and 167,000 total users. Those 167,000 users managed to vote just under 6 million times. With numbers this significant, we needed to ensure our architecture was highly performant and reliable. The first step of that architecture is the gateway. The gateway is a website that acts as a firewall and sits on top of the event hub. It filters out potentially harmful or malicious data and poorly constructed data. There are 3 specific areas that we look to validate: content type, header values, and message size. If the content type doesn't match what we're looking for, or we're missing any of the header values we expect, or if the message size is over the expected threshold, we throw that data out. We know roughly what size packets we should be looking for from the second screen, and this allows us to more easily filter out malicious data. I've said several times now that we throw out data, but that isn't really true. We throw out data in the sense that the Pulse will never see that data. However, we save it behind the scenes so we can further analyze it, both to help us improve any issues coming from the second screen, and also to beef up our defenses for new and unexpected attacks. The first of many benefits of the gateway is that it lets us keep the connection to Event Hub open at all times, rather than closing and opening it. This makes it far more performant. And then to further boost the performance, we can place an Azure Traffic Manager in front of the gateway to better handle load. Now, the final and most important benefit is that it keeps bad data from the Event Hub. Any data that goes into the Event Hub must come out, and bad data can cause severe problems. So protecting against it is crucially important. The knocks against the gateway are very minor: additional complexity and latency. Through our own testing, we found that the gateway added roughly 16 to 50 milliseconds of delay. But given the importance of this piece, that slim latency is more than acceptable. Keep in mind also that any additional piece you add is going to add both complexity and latency. So this is going to be a problem no matter what the individual component is that we're looking at. It's just a matter of to what extent it's going to affect your system. Once the data gets past the gateway, it's added to the queue in Event Hub. Event Hub is a service that collects and stores millions of data points. It handles vast quantities of data streaming per second while offering low latency and configurable data retention policies. It also uses elastic scale to better handle variable load spikes. This is especially helpful during events where we could potentially see random spurts of users. The best example of this was during one of the pulses for the presidential race, where Anderson Cooper mentioned voting on the pulse, and we got roughly 20,000 extra users within the space of a few seconds. Now, the greatest benefit of Event Hub is that it has an incredibly high ingestion rate. Through all of our testing and live events, we came nowhere near the level of scale it could handle. It's designed for this type of scenario, and it performs exceptionally well. A secondary benefit is that there are multiple consumer groups for the Event Hub. These groups allow for multiple streams to handle the same exact data. We use these streams to both cold and hot path the data. The hot path is key to our real-time data handling, while the cold path allows us to further analyze the data post-event. Unlike the gateway, though, there are a few more significant hurdles with Event Hub. The first of these is checkpointing. As you pull data off of the Event Hub, you have to drop a checkpoint as you go, noting how far you've gotten through the data. This means that you have to find an optimal number between potential data loss and throughput. The more you checkpoint, the safer you are, but the slower you go. The less you checkpoint, the faster you go, but you also risk losing data if your worker goes down. Scaling is also very painful since you can't scale without deleting the Event Hub. You need to plan ahead for these scenarios. You're going to have to shut off your ingress, wait for the aggregation worker to process all the data, and then finally upgrade the Event Hub and scale the throughput. And then finally, there's no local debugger. This causes an issue on teams with multiple developers who share the Event Hub. It's easy for them to steal each other's messages, and it's incredibly difficult to track issues. The data inside the Event Hub is pulled off by the aggregation worker. The aggregation worker is a worker role within the Azure Cloud Services architecture that pulls the data from the Event Hub and then validates the legitimacy of that data. You might be wondering why we have an additional validation layer here, and it's a fair question given that we already have the gateway for that. But as I mentioned earlier, the gateway is somewhat of a dumb validator. It doesn't have the same level of access to the pulse as the aggregation worker, so it's far more limited. The aggregation worker will match that the data being pulled out of Event Hub matches the pulse in a variety of ways. For example, it matches that the demographic IDs match those of the pulse itself. That means you can't vote on demographics that don't exist. It also validates that the vote comes in during a valid interval, so you can't vote before or after the pulse was live. Now once it validates this data, it then pushes the data into SQL. SQL will return a delta of the upsert, and then only the deltas are added to the caches and SignalR. This keeps the pipeline streamlined since it's only accepting new data. The benefits of the aggregation worker is that it's incredibly low latency for the internal communication within the worker itself. All the data it needs is present. Unfortunately, because of this, it's somewhat of a monolithic design, so everything is in that single worker, which means you can't individually scale the size of the VM for each component's needs. There's also no local debugger for the service bus, so you have to use an Azure service. If multiple developers are working on the same project, you run into the issue of stealing each other's messages, similar to what we were seeing with Event Hub, so it's hard to track issues. But a little bit of a pro tip here. There are service bus topics that you can use to help sift through the data. Those topics are properties you can add to your messages, so it's not going to solve the issue of stealing messages, but that way when you do see messages coming in, you can tell if they belong to you or somebody else. Unfortunately, because of the monolithic design, it also requires a full deployment no matter what component is updated. If you have 5 components and only one is updated, you still have to update the entire thing at one time. There's also potential for one component to crash and take the rest with it. Obviously, we validated against this as best we could, but there is still cause for some concern. Now, as I mentioned, there are 2 separate data paths for the aggregation worker, SQL and Redis cache. SQL is our long-term source of truth data storage. It will deal directly with the aggregation worker and the producer screen, whereas Redis is an in-memory data structure store, which is used as a database, cache, and message broker. It offers built-in replication and high availability. It's the point of contact for both the second screen and the external API. Now, SQL's benefit is also its negative, and it's the only part of our architecture that shares the negative and the positive. And that negative and positive is that it's a relational database. In hindsight, we probably would have used a document database, but realistically, this is more of a personal preference than anything else. Like I said, it's the only piece that could be interchanged with a different solution for minimal impact. It's more about comfort, and you could easily use something like MySQL, RethinkDB, or DocDB. You're not inherently tied to SQL. Redis, on the other hand, had much more defined benefits, the first of which was high performance. Because of the Redis engine, the cache is very low latency and has a high throughput. It also means you have a separate distributed cache layer, which allows the data tier to scale independently for an efficient use of computational resources. Equally as important are the pub/sub mechanics, specifically the pushing of data. There's a much lower latency to communicate with the security processes, and those processes get the data much sooner. Because of the push mechanics, we no longer need to pull data from SQL every X number of seconds. We can wait for the change metadata to come to us and get only the updated data and not the entire structure. The only real issue with Redis is in development. It's hard to sift through the data via the available tools. There are potentially hundreds of thousands of entry points, and it's hard to get the data you're looking for. But this is a headache that is more than bearable for the speed and reliability we get in production out of Redis cache. The final piece of this flow is SignalR. It's a library that allows bi-directional communication between the server and the client, with the servers pushing content to the clients as soon as it becomes available. Behind the scenes, we use a Redis backplane for distributed messages to keep the servers in sync, ensuring that each user gets the messages they need. The benefits of this, most obviously, are that it's the best available solution within a .NET environment. It's also very easy to set up and very easy to consume. Unfortunately, it also requires small packets and less frequent messages being sent. And in the area of messages, they're not always received in the order they're sent, which can lead to messages getting out of order. Lastly, state handling has occasional issues. It says you're connected even though you're disconnected. So there's not really a good way to reestablish your connection after it's lost and the retry limit is hit. The only piece of this solution that's a little bit outside of the realm of everything else is our blob storage CDN solution. So a producer saves a file or image, which is stored in blob storage. The second screen calls the CDN to then pull that data from blob storage for quick access. Again, every piece of our application is designed for performance, and the file storage is no exception. To recap, when you vote on the second screen, your vote goes into the gateway where it's filtered out. Assuming it passes validation, it's then dropped into the Event Hub queue, which in turn is pulled off by the aggregation worker. Once the aggregation worker properly validates it, it pushes that data to SQL, Redis, and SignalR. As needed, that data then goes to the external API, the dashboard, and back to you with the second screen. Now keep in mind, and I can't stress this enough, this all happens incredibly quickly, within a few seconds. So the data goes from you all the way through our architecture and back to you very, very quickly. All right, so we have this architecture that we've pulled together, and we feel it's pretty solid. But how do we know? We needed to come up with a way to effectively test our architecture in the real world before we had the scale of a real event. With that in mind, we developed a plan to create a testing package, affectionately named the Zombie Horde. We would build a desktop application to set up a test package, which creates and maintains thousands of headless testers. A headless tester is a self-contained testing user wrapped inside of a Docker container image. Its core goal is to act the part of the user as closely as possible, and we accomplish that via Node.js and Phantom.js. Node.js realistically doesn't do much beyond kicking off Phantom.js, while Phantom.js is the bread and butter of our testing application. It's a headless WebKit scriptable with a JavaScript API, and it's optimal for headless web testing. So we use it to simulate real user interaction. That means it's going to go to our site, it's going to download resources, it's going to act essentially as a real user would act. With this setup, the process of testing is incredibly simple. You hop on the Horde Manager app, set up your test scenario, your start time, pulse or pulses you want to hit, etc. You request a number of containers, and then you unleash the Horde. Now, one of the features that we most appreciate is the ability to test against multiple pulses at the same time. This gives us great insight into how the system would handle if we were running pulses from multiple large providers at the same time, like MSNBC, Telemundo, and CNN. So to show you how this actually looks in the real world, I'm going to go ahead and switch over to our Horde Manager. For those wondering, this is actually built in Node WebKit and uses Handlebar as its templating system. So when you come in, you're going to see this main screen. This is the scenario runner. I select our production environment that I want to hit. I already have an active pulse I'm going to vote against. So I'm going to go ahead and say get pulse data. So this will get the base metadata that it needs to run the headless test scenario. I'm going to say I want 100 different test instances. So that's 100 different users for this test. I'm going to select the start and end time. I'm going to go with something actually in the past. So that way, as soon as the instances turn online, they're going to go right away and start voting. And that's really all I need to do. If I really wanted to, I could actually go into sentiment and give very specific details. So I could give a likelihood of participation. If it's at 100, that means you're going to vote at every interval. If it's at 80, obviously it's 80%, et cetera, et cetera. The goal of all these details in sentiment is to help us get very specific scenarios. So if we want to test more real users or an overall load, it gives us a lot more control over that information. So now that I've done that, I'm going to go ahead and create these instances. So very quickly, you can see it's kicking off 100 different instances. And if I switch over to DCOS and Mesosphere, I can see in my dashboard that those 100 tasks are already trying to run. One of the really cool things about DCOS and Mesosphere is if it doesn't actually get to that 100 tasks, it's going to keep trying as hard as it can to get all of those up and running. So it's got a great error handling system. And if I go to my live poll, you can actually see that 99 of those users are online right now. And I'm already getting the votes coming in very quickly. If I refresh here, you should actually be able to see the graph coming in. You can see that down in the bottom right corner here in just a moment. There you go. So obviously this gives you a decent interaction on just a few users. And in a lot of scenarios, we would run a few thousand over the full course of the pulse. But if I wanted to start spiking it up little bit by little bit, I can just kick off 500 more here. And you'll see that those start coming in very quickly again. And it's going to get up to 600 here pretty quickly. So realistically, my only limitation during this scenario is the resources of my Azure scale set. So you can see it's got 328 tasks running, 200 staging. So its overall goal is to get as close to 600 as it possibly can. And then you'll Start to see those users popping up here as well. Now at our max capacity, we're actually able to get about 300,000 test users. So this really helped us feel comfortable going into some of our larger events because we knew we could handle a pretty large scale load, both as spike traffic and as extended traffic over time. I've covered a fair amount, and now it's time to wrap up with a few final thoughts. The first is a couple different resources. These are the ones out of all the things that I talked about that I felt were probably the most useful or helpful or interesting. So it's just links to Event Hub and the Redis cache and SignalR. Node.js and Phantom.js to me were two of the coolest things we did on this project, building those headless testers. So I highly recommend checking out Phantom.js and seeing what it can do for you and how you can use it to better simulate user interaction. And then in closing, I just had a couple final thoughts. The first is when you're working with architecture, you obviously want to plan ahead, but not too much, especially if you know going in that you're going to want to be able to handle the type of load we did. But at some point, you need to test your architecture in the real world. No matter how long you spend planning it and thinking it out and wargaming it and all that jazz, you're not going to get a good feel for it until you actually test it in the real world, whether that be testing it yourself or throwing it into the wild and seeing what happens. And then finally, log early and log often. This is great for a number of reasons, especially when you're working with architecture. It gives you a good feel for how your architecture is handling in the moment, things you can do to help improve it, and then it gives you a good feel for how your architecture evolves over time and how performance increases or decreases based on the moves that you make. Alrighty, well that's all I have for you today. Thanks for watching this video, and I really hope you enjoyed it. If you have any questions either about the Pulse project or GMR marketing, I'm more than happy to answer any and all. You can find my email down below.